Now we'll see B plus trees. B plus trees is a variation in B tree. That means, so B plus tree is almost B tree, but we have some improvements over there. So what are the improvements we will see? One important improvement is, so we have separation between nodes, internal, external. In internal we'll have keys comma tree pointers, no data pointers. In only leaves, external node means leaf. In leaf you have keys comma data pointers. That means whenever you want to find out a value for whatever, we should come to definitely external nodes. That means leaves. So always search will end up at leaves. But whereas in B tree your search can end up anywhere. That is the difference. So why that difference we will see. So when you have this difference, what happens in the first level? Example, let's say this is your root. Assume that let's say this is now internal node. If it is internal node, you will be keeping only keys comma tree pointers. When you do that, what happens for a particular or fixed block size, it will have, you can pack more number of entries than in B tree. Correct? In B tree you have to pack keys comma tree pointers comma record pointers or data pointers. Here you need to pack only keys and tree pointers, then the number of entries will be increased. When the number of entries are increased, the number of pointers will be increased. When you have more pointers, then that such tree can point to more number of nodes in the next level. So if you have more number of levels in that node, then again you can have lot of pointers, then quickly you can index the file. So what I want to say is, if you have B tree, if your file size something X, then if B tree requires 10 levels to index your tree, then B plus tree definitely requires less number of levels. The reason of the reason is branching factor. So I can say this tree, otherwise B plus tree has more branching factor than B tree for same terms and conditions. You remember it. So now we'll see how such tree can be maintained, and how insertion takes place and how deletions take place and how we index using that tree. For that we should focus on these details like internal node. So sir, what is order then? So usually in B tree we have order, right? Here also we have order, but we have order for internal node separately, order for leaf separately. So let's define what is order P internal node and what is order, let's say Q, order Q leaf node. Whenever I say my B plus tree is order, has order P internal nodes, then always we should bother about two things. One is minimum condition, second one maximum condition. Minimum condition will be like this. You have at least P by 2 3 pointers and you should have at most P 3 pointers. Okay, remember it. P 3 pointers, P by 2. Now if it comes to keys, P by 2 minus 1 keys and P minus 1 keys. That's obvious. So it is similar to B tree condition, right? Now, and one more thing. This minimum condition is only for non-roots. That means for root there is no such restriction, because root can have any number of keys and any number of pointers. Of course, but max condition is for everyone. There is a restriction on max condition, but there is no restriction on min condition, right? So I will tell you the reason. So what is the reason for that is, in B tree also I did not explain you what is the reason. So whenever you do insertion process initially, whenever your tree is empty, then you will have only one root with 0 nodes, correct? And assume that, let's say, that is not at all a tree. Whenever we add only at least one node, then only that will become tree. Let's say if we follow this assumption, then to create a tree with at least one key, then you should have a root with only one key, correct? So sometimes it is required, without that you can't create the tree. That's why root doesn't have restriction that root should have at least these many keys or whatever. Example, if it is order 10 B tree, then root cannot have that kind of restriction that it should have at least 5, because sometimes we will keep one node or two, one key or two keys. So in the same way, in B plus trees also you can understand that. So now order Q. So what is order Q leaf? Same idea, but here why there is a difference order here and different order, I will tell you. So here you have keys and data pointers, right? That's why order is differently defined. So we are going to define order with keys. So here for me entries, focus is on, here pointers, right? Here focus is on keys. So I say that whenever it is order Q leaf node in B plus tree, minimum number of keys and here maximum number of keys we should see. Again root has an exception. Other than root, every leaf should have p by 2 keys and maximum p keys. So minimum p by 2 keys, maximum p keys. That is a condition for order cube, in especially in leaves. Now let's summarize. So you have two kinds of nodes. One is internal, second one external. In internal, minimum p by 2 pointers, maximum p3 pointers. When it comes to external nodes, so we should talk about keys, then minimum p by 2 keys and maximum p keys. In both of the cases, so there is a minimum condition only for other than root. Root doesn't have any such kind of thing. Apart from that, everything is same. So B tree and B plus tree are almost same. There is one more point I am going to tell you. Other than that, so B tree is a search tree. B plus tree also search tree. Now one more thing, B tree, in B tree keys are ascending, I mean they are ordered in ascending order. In B plus tree also keys are ordered in ascending order. And in B tree, so leaves are all in the same level. Here also in B plus tree, leaves are all in the same level. That's it. So finally I can say that this is the only major distinction. And one more thing is, usually the leaves are connected. I will tell you the reason for that, but remember that, so all your leaves, let's say this is your B plus tree and these are all leaves, then they are all connected either one way or two way. You can use double linked list, otherwise single linked list. If it is double linked list, then in everywhere, in every node, see, example, focus on this node X. We have to maintain left pointer, right pointer. That means we have to maintain two extra pointers. Similarly, we can have single linked list also. I mean, it's okay, like we can have single linked list and still we can, do our job. So what is that? So if it is single linked list, then, so this first node will be pointed to the second node will be pointed to third node. In that way, only one directional. So both of them will work, and there is no compulsory thing that we should have two pointers or one pointer. Either you can implement in a double linked list fashion, otherwise single linked list fashion. Now we'll see such details one by one. First of all, let's take one order tree. That means sometimes what happens in the exam, they say order 6 B plus tree or order 5 whatever. Let's say order 4 B plus tree. And they don't mention this order is for internal nodes or leaves. If they give only single order, then how to understand it? Simple. So these are all technical issues, like when you are implementing, we should take care of them. But in the problems, if they give this kind of variations, order 4, but they did not mention, then you have to take for internal nodes order 4, external node order 4. That is the only way we can understand that problem, right? So let's do that. If it is order 4 B plus tree, then in internal node you will have 4 by 2 pointers. That means minimum 2 pointers, minimum 2, maximum 4 pointers. Whenever you have minimum 2 pointers, minimum keys are only 1 key. You can have minimum 1 key, maximum 3 keys. With respect to keys, this is the way. Now let's come to leaf definition. In leaf, if it is order for leaf, then minimum keys are 4 by 2 and maximum keys are 4 keys. So here 4 keys and 4 by 2, 2 keys here. In that way we can understand this B plus tree order. Whenever order is mentioned, but not whether it is internal or external, take that order for everything. That's it. Okay. Now we'll see how to create this kind of B plus tree. So order is given. Let's say order 3 internal node, order 2 leaf node. Then how to create a tree we will see from the scratch. Since it is order 3 internal node, what we do is we first of all understand what is the minimum condition, maximum condition. So minimum pointers will be 3 by 2, correct? So maximum pointers will be, and this is of course sealed, so maximum is 3, right? With respect to keys, if you see the same thing, I am writing with respect to keys. So keys for internal nodes. So since there is at least there are 2 pointers, 3 by 2 is 2, then we get 1 key. Here maximum 3 means here 2, right? We know the relation between that. Similarly, let's try to understand order of leaf nodes. For leaf, minimum, now entire story with keys. So minimum 2 by 2 keys, which is nothing but 1 key, maximum P, that means 2, right? So 2 keys. So remember. So I have fixed internal node order and leaf order such a way that everything is same. Okay, that might not be true always. For our convenience, we did it. So from now onwards we have to maintain minimum 1, maximum 2, but root doesn't have any such restriction, right? Minimum restriction. Let's begin. What if suddenly user enters the first data into the table like this 1 comma a in somewhere. Let's say this is block number 1. So for time being we assume that we have only block pointers. Remember one thing, so whenever you have a data pointer, that data pointer may be record pointer or block pointer. At this moment assume that we have only block pointers. So let's say this is B1, otherwise I can give that this is a record and its record pointer is R1, right? So how to create a B plus tree we will see. First of all, create a leaf. This is leaf because it doesn't have any child. Now in that one, write an entry like this. So you know that leaf should contain the data information. That means leaf has to provide where is each record. Since you have a record in B1 block and especially record pointer R1, we write like this 1 comma R1. So this is idea. So this is leaf, you know the structure. Only keys comma record pointers. Simply write key followed by record pointer. In implementation we do like this. Key some memory and record pointer some memory like this, and every node has some capacity, right? Maximum condition. What is that? In a node we should have how many keys? Minimum 1, maximum 2 keys. Yes, we are satisfying that. From now onwards I don't show record pointers. You understand that yes, we have record pointers, right? Now 1. Next, what if I insert 2 comma b, whatever? So order doesn't matter. So what I do is in leaf I will first of all, I have only one node, I search for 2, there is no 2, right? Then we write here 2. So in the searching process I understand that 2 should be right side of 1. So now there should be, of course, you know, there is no pointer to further nodes. We know that it is leaf. Only record pointers we have to write R1, R2. But I don't want to show because if you show that, the picture will be clumsy. That is what my worry. Otherwise everything is proper. Now we'll see. Let's insert 3 comma c, which is new information. If I add 3 here with record pointer, so maximum condition will be violated because we have some restrictions on the keys, like number of keys, right? So that's why this is a problem. Then how to solve it? So whenever you have such problem, what we do is in implementation or in theory, I can teach in a theoretical way, otherwise implementation way. In theoretical way, simply divide this into 2 parts and create 2 separate nodes. If you come to implementation, the same thing I can say like this. This is one actually block. So remember one thing, every tree node usually we keep in block. We know that we have studied in B trees. So this is, let's say, some block, let's say B5 or something. Then create a new block and half of the keys we have to transfer to right side. So here we have 1 comma 2 comma 3, right? Then half means because in 1 2 3, so I can't divide exactly into half. That's why I send 2 comma 3 to right side along with their record pointers. From now onwards I don't show. This is also leaf. Now I create one more page or block. See, in implementation 2 new blocks got created. So here what I do is I am going to keep these 2. Just try to understand. After that we'll see the reasons. So 2's left. Now this is going to be internal node. So that's why 2's left we have to link like this, 2's right we have to link like this. Please recall what is internal node. Internal node will have keys comma tree pointers. What was the purpose of maintaining tree pointers? For further searching, correct? So if you want to go to, and if you want to search for left side up to this pointer, right side up to this pointer, right? So this is the entire story. Now internal node keys. Example, let's search it. You want to search 3 comma c, right? Simply search for value 3. 2, then go right side, then we come here, search again for 3. You will hit here first time, and we know that it is leaf. Somehow we keep a simple marker like this. 1 means leaf, 0 means internal node. In that way, so we can take care of technical details. It's not a issue, right? So now since it is a leaf, when you search it and if you get the value, you should say that we get it. Now see, 2 and 3, we got it, right? So when you get it, what you have to do? We will have record pointer here for 3, directly take it and you directly come to this record and fetch it. That's it. Now example, you are searching for something around 0. When you are searching for 0, come here 2, then go left side, we come here. Since it is leaf, we have to stop searching. If you get here, successful, otherwise unsuccessful. So now see, 1 which is greater than 0. So your search is unsuccessful. Simply say that there is no 0. Now if you are searching for 2, start here. Yes, this will match, but it is not leaf. That means though you know the key here, you don't know the data pointer. So all the data pointers are only at leaves. And one more thing already I told you. So these leaf nodes are connected. We will see the reason. It's suspense for this time. Now 2 to 1, 2 to 2. So 2. So remember one thing, for smaller values we go this side. For bigger than or equal to, we come this side. So this is not compulsory. We can do alternative also, like all the values which are less than or equal to this side, all the values which are greater than to this side. We have two alternatives. Anything is okay. So in the exam, if they don't mention anything, try both of them. We don't have other option. Now let's see. Example, you are searching for 2, but I am not using this method now because I ordered my elements such a way that so less than, strictly smaller values this side and greater than or equal to this side. That's why I come here and I will hit here and I will take the data pointer of 2 and that will show this one and I fetch it. In that way B tree is implemented. Correct? Now remember one thing, try to ensure that leaves contain all the record information, like all the table information, right? Let's add 4 comma e. If I add 4 comma e, so where we have to add? Always in the leaf, because this is a new record. To maintain this records information, where I can maintain this information only in leaf, then finally your search should end at, otherwise your record should end at leaf. That's why what I do is, first of all I search for the right position or right leaf. So start here, then if you search, always search ends at leaf, that will be the right position. 2, and for that, for 4 you come right side and here search for 4th position, 2 and 3 and this point, right? Since 4 is greater than 3, so we get here. But according to our tree conditions, leaf can have maximum 2 keys, but you are going to keep now 4. That is not possible. Then what to do? So here we have to apply again node splitting algorithm, right? So we will see node splitting algorithm clearly now. Already we have seen, but this time I am going to explain you. So in B tree node splitting is different and in B plus tree node splitting is different. How it is different we will see. In 2, 3, 4, what we do is, first of all we divide that node into 2 parts. So here 2 and here 3, 4. Now middle node is 3, then we send 3 to the next level. The next level is this one, right? So I will show partially like this. First of all we see partial tree like this. So in the next level we have to keep 3 along with some other values, doesn't matter for me. So 3's left will be 2, 3's right will be 3, 4. Now 2's record pointer will be along with 2, 3's record pointer will be along with 3, 4's record pointer will be along with 4. So every node, every key has record pointer in the leaves, right? So 3, this purpose of this 3 is only for indexing the tree. That means for showing the directions. That's why we require to keep 3 here and here, right? So now the same thing we do for this tree. So here initially we have 2, right? What I am going to do is send 3 to the next level. It comes here. Now we have already position for keeping a pointer here, keeping a pointer here, keeping a pointer. Now we use it. 2's left as it is 1. In between 2 comma 3 we keep dash, and after 3 we keep dash. We will see. Since we divided this node into 2 parts, one is 2, one is 3, 4, this 2 comes here. Then according to our logic also, we always keep values which are strictly smaller than 2 this side and greater than or equal to this side, right? Similarly for 3, strictly smaller than this side, greater than or equal to this side. That's why 3 greater than or equal to 3 are 3 comma 4. So meaningful, right? So this splitting, node splitting is perfect. Now this node splitting ensures 2 things. Your tree is B plus tree. Second thing, all the leaves are in the same level. Of course, that is again one more condition of B plus tree. So this is the final answer. Let's add one more, 5 comma f. If I add 5 comma f, what happens? We'll see. So search for 5, you end up here, correct? Then 3, 4, 5. Then again maximum condition is violated at leaf. Then send 4 up. When you send 4 up, already I told you the technique is like this. Only focus on 4. 4's left should be, see, 4 is going up. 4's left should be 3. 4's right should be 4, 5. That is the B plus tree idea. So If you see here, 2 is left, and in between 2 3, and after 3 and before 4 this one, and after 4 this one. So here we should write as it is 1, we are not disturbing that. So here 2, this will be the tree. But the problem is, when you do node splitting, we are sending one key to the next level. So then in the next level you might get this problem. What is that? That may be definitely internal node, and that internal node has maximum condition. What is that? Maximum we can have 2 keys, but now you are filling 3 keys. What to do? Same thing, whatever you did at leaf, same thing you should do at internal node. We send one more key to the next level. Since there is no next level, what we do is we send 3 to the new root. So this is now new root. 3 will have 2 pointers, and when we split here, you get 2 sub pages, I can say. In one we have 2, in one we have this one 3 comma 4, but don't keep 3 comma 4. Why? So why generally we copy the data is to maintain the data in the record, leaf pointers, right? So but here you don't require, because this is internal node. In internal node, why you need multiple 3s? The purpose of having 3 in the leaf is only to have the record pointer, correct? So now here you don't require it. Simply do like a B tree. 3 left is 2, right is 4. 2's left 1, 2's right is 2, 4's left is 3 here, and 4's right is 4 5. See here, the duplicates, if you see, the key duplication is only at leaves, but that key duplication is not required in the internal nodes, unnecessary. Okay, so finally this is B plus trees insertions. Very easy. But the only thing, the summary, in B plus tree, we have to use node splitting algorithm. We have other algorithm also I am going to mention. Let's say in node splitting algorithm, especially when a node contains more than maximum elements, we have to split it and divide that into 2 parts, then send the middle key to the next level, right? That is a node splitting algorithm. But if you split leaf, then we have to maintain a copy. That means whatever the key you are sending to the next level, that record pointer has to be maintained in leaf along with the key. That's why we do the duplication, right? So when 4 is sent to the next level, 4's record pointer to maintain, we have to keep key also. That's why, so we maintain the duplicates. And when you split the internal node, so we don't have that kind of reasoning now, so simply send 3 up. That's why the split will be 2 comma 4. That's what the 2 comma 4. That is the major difference between splitting leaf node and splitting internal node. Otherwise everything same. Now we will see one more strategy, that is redistribution. So what is that? So in redistribution, what we do is we don't do node splitting. The problem with node splitting is, if you see here, example, let's say you are splitting the leaf. When you split the leaf, then one element propagates to the next level. Because of that, again node splitting might occur. Assume that your tree has multiple levels. So let's say n levels. When you have n level tree, in the leaf level, if splitting occurs, then you are sending one node to this side, next level. Because of that, again this node may be more than full, then we again split it. In this way, the process may go up to root, and we split the root and we create the new root. So what's the problem, sir? If tree contains, let's say, log n height or log n levels, whatever, doesn't matter, approximately. So if your tree has log n levels, then in every level to do this process, we have to access the node, right? Like, so this page where it is in disk, then how many disk transfers we require? So many. For log n levels, log n disk transfers. That's the problem. We have to save lot of time. That is what our goal. Indexing's idea is that, right? So that's why when you do node splitting, you will be accessing lot of blocks in the database. We should avoid it. Sometimes we can avoid if you use redistribution. So in redistribution, so rather than splitting, we are adjusting the nodes in the locally, I can say. That means from one leaf to another leaf. We are going to see that. So because of that, number of disk transfers will be reduced. We will see. Now we'll see in various cases, how this B plus tree will be readjusted. First of all, we start with something around here. Let's say data is something 17. If I insert 17, search process we know that now comes here, then we insert here 17, then maximum condition is not violated, no problem, right? So that is the way we usually insert this kind of nodes of data. Example, let's say you are inserting something 25. So if it is 25, see, first of all search for 25. So go right side. Then since your data is equal to 25, then we have to come this side. We know that 30, since it is 25, we should go left side. So we have again space. So don't write 28, 25 after 28. We write like this: 25, 28. We adjust it, right? No problem. Now see, what if we insert 20? Search 1625. This is a pointer. 1820. Don't say that I stop here because it is not B tree. We don't have record pointer here. So further we have to continue. For 20, always we should go right side because of what was our model? Left side less than, right side greater than or equal to. That's the reason we are coming this side. So here, do we have 20? No, add it. When I add 20, so you get the problem. What is that? So node full. I mean more than full. So we have to split it. What is the middle element? 22. So 22 will be sent to this side. Correct? Let's do it. So whenever I send 22 to the top, you create here two subnodes. 21 thing, second one 22, 24. Since we have two boxes, we should not worry. The reason we are going to have one key here, that is 22. See this one. Then that will give you two positions, right? So when you add one key here to the next level, you get two spaces or two pointers. So 22 left 20, 22 right, 22 24. Now you got violation here 18, 20, 22. Then we have to resplit, correct? So here when you split 20, what happens? 20 will go to the next level, right? So we divide this into two parts. 20 is going to up. So this is one thing, this is one thing, correct? So 20 is going to the next level. And when 20 comes here, see, 20 will have two pointers, correct? 20 is right this side, 20 is left is this one, see now. So everything is adjusted automatically. Now 20 is left is this one, 20 is right this one, perfect. Because of this one, 20, so now again you got node full, then we have to adjust the tree. When you adjust the tree, then this 20 again will go to the next level. So 20, let's split it into two parts. See this one, this entire thing is 1, this entire thing 1, right? We have to adjust the pointers properly. This pointer belongs to 16's right, then link like this. And 25's left is this one, right? Everything adjusted properly. 20's left 16, 20's right this one. So automatically we follow the search key, search property. Now see, this is the final tree because of the node splitting. But what I want to say is how many blocks you accessed. If you see, you accessed here this box first, correct? It was one box. You accessed that block. Now see, you create a new block and you accessed it, and you access this block, new block, this one, and this is old block. You access this one in the process. You access this block, you access this block, you access this block. So many block accesses, right? So we have to avoid it. Then we can go for redistribution. We will see redistribution for this problem. Let's take same as it is. In this problem, let's say I am adding a new key, that is something 27. Let's say insert here 27. If I insert 27, first of all try for searching. 25, go right side, 30, 40, 27, left side of 30, come here. Then 25, 28, it would be here, right? Now if 27 is inserted here, the problem is, so this 27, because of 27 this node is more than full, then we have to do redistribution. Already we know node splitting. One more alternative is node redistribution. In redistribution, what we are going to do is, we are going to send this 28 to this side, whatever. First of all, to do redistribution, this node should not be full. If this is full, if you send one more key, then again here you get node splitting. That's why here only node splitting works, redistribution will not work. That's why in redistribution algorithm, if your sibling, and one more thing you remember, we only do these things with siblings, okay? So whenever you have a sibling and that sibling is also full, then go for splitting, right? So now we'll see a case where we are, let's say, inserting 13. If you insert 13, first search for it, 20, then go left side, 16, 13 left side, 6, 10 right side, then 13 comes here, right? Once you add it, so it is more than full. Whenever node is more than full, then we have to do redistribution with sibling. Who is the sibling of this node? Let me redefine what is sibling. Simple. Whenever a key has Keys are usually, let's say whenever a key has two pointers, then these two nodes are called siblings. That means for this node and this node, the parent is 10. So whenever you have a common parent for two nodes, we say that they are siblings. So these two are now siblings. These two are siblings, but these two are not siblings. Remember it. The reason, 5 nodes parent is 6, 6 and 12, 13, 15. These two nodes parent is 10, right? So we do redistribution with this one. See, this has space, right? Then we can apply redistribution, not a problem. If you apply that, so what I'm going to do is, so this is the right node, right key which we can send right side, left side. Correct? We can't send 15 this side, because if you send 15, then it will not be search tree. In search tree, so smaller value should be this side, bigger value should be this side. That's why 12 should be the right element. What I'm going to do is, first of all, I will tell you one thing. I keep 12 here. That's it. But the problem is, this anchor 10 will not work. Of course, right? We remove it because 10's left always smaller values. That's why we remove it. Because the purpose of, sir, if you delete it, you are losing data. No, I'm not losing any data, because all these keys in internal nodes purpose is only anchoring or directing the search. Then if that search, whatever the key you are using, if it is not helping you, simply discard it. The leaf nodes are very important because we have keys along with the record pointers. Don't delete them without reason. That's why this is only for anchoring. We can delete it, not a problem. But you tell me what to fix. Same thing. See here, 13 is the first key, right? If I keep 13 here, then it will perfectly work as anchor. That's why I select 13. See, 13's left is 12, 13's right is 13, right? Greater than or equal to, less than. Perfect. So this is redistribution. Understand? Now we will do redistribution one more time. Let's do redistribution here. Something you are inserting 18.5. Okay. Then if you are inserting 18.5, otherwise 20. So for 20, what happens, we'll see. 20, then go right. 25, go left. Come here. 20, go left. Right. So it's already there. Then we land up here. But our target is here, right? So if your target is here, then definitely it should be something, I can say 18.5. That's perfect. So let's use 18.5. If 18.5 is inserted, then search process 20 left side, 18.5, 18.5 right side, 18.5 with 18 right side. We come here, then we insert 18.5 here. When I insert 18.5 here, then let's rewrite it. It is 18.5. Node is more than full. Then what to do? Redistribution. If it is redistribution, we have only one sibling, this one. Then we try to transfer the key. For that, anchor is 18 here. If so, and the element is 18, this one. If I keep 18 here, then you get a problem, right? Let's do first this one. This anchor will not help you. That means it's not working properly. If 18 is anchor, left side should be smaller than 18, but we are not using, satisfying that. That's why remove 18, not a problem. Keep whatever you want. Always this would be the best thing. In the resultant node, after transferring the key, the first key should be kept here. That's it. 18.5 is right is 18.5, 18.5 is left is 18. So this is redistribution algorithm. If you see redistribution, really it works, then how many nodes you are accessing? Example for 18.5, I access this node, one block transfer, because you access this node and you accessed just parent. So one more, right? 3. But if you have, let's say 20 levels in your B plus tree, and in the worst case, let's say if you are using node splitting, then so many blocks we have to visit. Correct? Already we have seen how many blocks we have to visit. Think about it. Take a very big tree and try to do node splitting in, and imagine otherwise take the data such a way that you have worst case situation, and observe how many block transfers you are doing. That's why redistribution usually will have very less number of block transfers. But, and one more thing, it doesn't mean that node splitting is awkward, otherwise inefficient. Then in node splitting also, that node splitting propagates to root only very rare, like in very rarely. So why are you thinking like this? Always whenever here node splitting, in the next level node splitting, in the next level node splitting, that might not be the regular case, right? It is very rare case. That's why node splitting can be used, otherwise redistribution. We can't say that redistribution outperforms node splitting, otherwise node splitting outperforms redistribution. We can use both of them, like it depends. We can't say that one of them is best, otherwise one of them is worst. We can't say, because the advantage of node splitting is, example, let's say you use redistribution. When you do redistribution, then you just consult your neighbor, let's say sibling. When you consulted your sibling, let's say imagine you have two siblings, okay? Then you consulted sibling number one. My dear sibling, can I send a key to you? He said, I am already full. Then you will consult this one. Again, he said, I am already full. Then what? Again, we have to go for node splitting, correct? So I can say that sometimes even in redistribution also, we have to visit this block and this block. Then later you realize that there is no space. Then again we have to do node splitting. That's why I can say that each and every each algorithm has pros and cons. But overall, redistribution is good. Okay.